Okay, so in this topic, in this video, what I wanted to do is I wanted to look at some of the problems from 6.2, and I could do some of them. I'm going to show you guys an example of how to do some of them if you were going to use the methods of 6.3. So it's kind of focusing on problems from 6.2, but I'll also say if it was something from 6.3, how would you approach it? For example, say number 3. So in 6.2 number 3, and again, this is not just what number 3 says. I may modify it so it would include also problems that are methods that are used in 6.3 as well. So I'm going to modify this or add to a problem a little bit. So you have y equal to square root of x minus 1, y equal to 0, and x equal to 5. So those are the boundaries of your graph. So again, the problem says about x-axis, but we'll play with that a little bit. So the shape, the region that they're talking about is this square root graph. This is 1, this is 2, 3, 4, and 5. So it will be like this one. So this is x equal to 5 line. This is y equal to 0 line, and this is a graph root. So this will be your region. So they say about the x-axis, which is y equal to 0 line. So originally what the problem is asking you to do this using this washer method and rotate it about the x-axis. If you remember from the chart I gave you guys yesterday, if you're rotating about x-axis or parallel to x-axis and you're using the disk or washer method, then you use dx as your measure. So we know that it's going to be dx. It is a disk washer method, so it's going to be pi radius outer radius minus inner radius, and radius is the distance from the axis of rotation, which is going to be this for every x. And if you're trying to figure out what the shape looks like, which is not necessary for your calculation, but for visual effects, this is what the shape looks like. So your circles look like this. So your radius is going to be the function itself, which is square root of x minus 1 squared. Again, notice that x and dx. So I have integration with respect to x, and my function is with respect to x. So I just get pi x minus 1 dx. Done. Pi r squared delta x. Now, the same problem, if I were to do this using washer method, I'm sorry, cylindrical shells method. It's not washer because you're going to have a hole in it. But anyways, if I were to do this using cylindrical shells method, which is a topic from next section, but let's just play with it, right? So it's going to be for rotating about the x-axis for shells method is going to be dy. So my measure is going to be dy. Oh, sorry, I forgot the bounds here. Sorry, the bounds are from 1 to 5. Okay, but if I'm going to do cylindrical shells method, it's going to be 2 pi radius times height, and of course it's dy. Y bounds are from 0 to square root of 5 minus 1. I mean, again, plug in 5 for x, you get 5 minus 1, which is 4. Square root of 4 is 2, so y goes all the way up to 2, so 0 to 2. Your radius is how far away are you from the axis of rotation, which is, again, in this case, is going to be y. So y keeps track of how far away you are. So this is whatever y value is, that's my radius. So it's going to be just y. Height, now this is the part you have to be careful about because it's, again, as I said, maybe if you haven't done this problems before, it's a little bit tricky. But height is this height. This is the height, right? The distance from 5 to the curve. So the distance from 5 to the curve is height. Okay, so the distance is going to be 5 minus, and your curve, although it is y equal to square root of 1 minus x, you have to write it in terms of y. So y squared is 1 minus x, and x is equal to 1 minus y squared. Okay. So 5 minus the graph of the function, whatever the graph of the function is, the equation of the function is, in terms of y. And again, oh, sorry, it's x minus 1, sorry. That's why I felt like it doesn't look right. Yeah, very good. Now, if you on a test, if you make errors like that and you catch it later, just let me know that you noticed that error, and then fix it, and if you have time. But definitely let me know that you found out that there is something wrong with your picture. So once again, radius times height. And the height is not going to be always the function. Sometimes it's like this, 5 minus a function and such. This is a Shell's method. And this is the disk method. Now let's make this exciting, more exciting. So again, same function. Okay, same function. Y equal to square root of x minus 1. Region, the same region. X equal to 5, x equal to 1. This. And now let's rotate it about the y. Again, this is not the problem. The problem was just the first part of it. This was the answer to the question. But I'm just doing other cases just to show you guys how to approach this. Let's rotate it about the y-axis. So we expect something like this, again, by rotation. Yeah. And I'm going to do the disk method, but in this case, it's going to be the washer method, because there is going to be a hole. There's going to be a hole in the middle, right? So again, if I'm rotating about the y-axis, going back to my chart, I'm doing a disk washer method, and I'm rotating about something parallel to y-axis. So I'm going to have dy. So now it's going to be dy. I dy. Y obviously goes from 0 to 2 again. Outer radius is uniformly 5 throughout. Inner radius is going to be this function of y, whatever that function of y is, which we calculated earlier here to be a y squared plus 1 squared. Outer radius minus inner radius. Outer radius squared minus inner radius squared. This problem actually begs to be done with cylindrical. So this is a washer method. Again, remember, washer and this method are the same thing. It's just whether your shapes turn out to be disks or washers. Do they have a hole in the middle for washers or not? Basically, if I take this rotated version of this and look at it from the top, it looks like this for every single one of those. That's the washer. Now, if I do the Shell's method, then because I'm rotating by the y-axis, it's going to be dx, 2 pi. X goes from 1 to 5. Radius is the distance from the axis of rotation, which is just going to be x. For every x is just that. Height is going to be the function. Students ask, how do you integrate this? Because again, it's not common. So let me go ahead and finish this one. So I get 2 pi 1 to 5. I'm going to do a x root x minus 1 dx. What I'm going to do is I'm going to do what we call u sub. You guys remember that from section 5.5. So I'm going to let u be x minus 1. The u, of course, is dx, no problem. But then when x is 1, u would be 1 minus 1, which is 0. When x is 5, u would be 5 minus 1, which is 4. So it's going to be 2 pi integral from 0 to 4 square root of u du. And then x that's sitting here, from this equation, x is u plus 1. So power rule again. Add 1 to the power, yeah. And 4 to the 5 half is square root of 4, which is 2 to the 5th, which is 32. 32 times 4 times 2 is 64. That's just a arithmetic. And then you can just calculate that. Okay. So again, now I did this 2 methods, Shell's method and Washer method. And you can check the answer. They should get the same answer for both of them. Okay. Now let's do that a little bit differently. Let's same graph. Let's say y equal to, and again, at any point of this video, if you want to review, just watch it again. But I try to cover as many questions as we can. Of different cases. So let's go again with the same thing, 1 minus x minus 1 as your function. Again, x equal to 5, y equal to 0, same thing. But let's say you rotate it about x equal to 6, for example, just for fun. So now your shape looks like this still. And 6 is this. Okay. Okay. Now let's do, I guess, this method. What in this case would be Washer method first. Okay. So, and again, remember your shapes are going to look. This is a solid. That's a rotation of, yeah, that piece. So it's I don't know. It's a cake with a hole in the middle, if you want to think about it that way. So the radius out. So it's going to be again integral pi. I have to figure out the bounds, which is actually right in front of me. But the outer radius square minus inner square. Since I'm rotating about something parallel to y-axis, I go back to my chart. If it's parallel to y-axis and I'm using disk method, it's dy. So it's going to be dy here. Outer radius is this. Again, remember, you always go with your original graph and not the graph that you get from rotation. So the outer radius is going to be 6 minus the function. So it is 6 minus y squared plus 1 squared. Remember, I have to write it in terms of the function y, variable y. Inner radius is just this, which is 6 minus 5, which is, I write it as 6 minus 5, but 6 minus 5 squared, which is 1 squared. Again, remember, this graph in terms of y is x equal to y squared plus 1. And y goes from, once again, 0 to 2. That's it. Just power rule all the way through. Now, if I were to do this with Shell's method, then I'm going to have integrate with respect to x, because remember that's the difference, because I'm rotating about something parallel to y-axis. So I integrate with respect to x. X goes from 1 to 5. Radius, now you have to be careful. Radius is no longer x. Radius, if this is your x, radius is 6 minus x. X measures from here to here as x. From here to here is 6. So the radius, which is the distance from the axis of rotation, is 6 minus x. And height would be the value of function, which is now square root of x minus 1. Again, for this one, you will have to use substitution to solve. So that's how you would do that one using Shell's method. A good check is to check the answers. They both have to give you the same answer, obviously. Okay. Now, let's do just one more of these, and then I'm going to do something a little bit different. So let's the same function again, same given function. 5, this 1, this is square root of x minus 1. And let's rotate it now. Y equal to -2. Again, the shape or the accuracy of the shape is not as important as the algebraic expression you write or the calculus of what you do. But all right, so let's do it using yeah, let's do the disk washer method again. It's washer because it has a hole in the middle. If it's washer parallel to x-axis, it's dx. X goes from 1 to 5. Pi outer radius now it's going to be the distance from the rotating axis. So it's going to be the value of the function minus -2, which is going to be +2. And the inner radius is a constant 2. So that's how you get the, again, remember your washers look like this. Inner radius is always 2 throughout because as you go from outer to top, it's always going to be the same 2 as your inner radius. The outer radius changes based on your value of your function. So okay. Now, if I were to do this using Shell's method, I'm rotating about the x-axis, so it's going to be dy. I mean, parallel to x-axis, it's going to be dy. Y goes from 0 to 2, obviously, from before I showed you guys. 2 pi. Radius is a distance. So if there is y here, this is y. Again, if this is y, the radius is y minus -2, which is y plus 2. Because y is this distance, -2 is this distance, so y minus or 2 is that distance, so y minus -2 or y plus 2 is what you have to consider for your radius. Again, y is this part for every y. This is y, this part is y, and then this part is 2, so y plus 2 is your radius. Radius is a distance from the axis of rotation. And then height is going to be the same height we discussed, 5 minus the value of the function. So 5 minus y squared plus 1. That would be the Shell's method for this. Okay. The computation are mostly either U sub or power function. So that's okay. I hope it's okay by now. Okay. So this was a question of just kind of like a recap the similarities and differences between Shell's method and this washer method. I was also asked from some of you guys to answer questions like 48, 49 and such, which has to do with calculating the area, the volume. They may or may not be rotation, but I guess 48 and 49 are also rotations. But so if I look at say 48, the shape that they offer is this. It's a frustum. We call this a frustum. You'll see it again when I talk about surface area later. The topic will come up. And this is H. This is lowercase r, and this is capital R. So the way you're supposed to do it is not unlike what we did in calculating the area of a volume of a cone. You're supposed to, or you're suggested to let this sit on the x-axis. You go from R to capital R. So if I can find the equation of this line, then I can find the area of the cross sections, and then I can integrate. So first I need the slope. M is equal to R minus R over H, rise over run. your y-intercept is 0r. So y is equal to r minus r over h x plus b. And if I plug in 0r, r is r minus r over h times 0 plus b. Again, your y-intercept is that, so you don't really have to do all this, but you can just say r is equal to b. So the equation of that line, and again, however, how fast you can find it, that's perfect. You don't have to write all the steps I write. So y is equal to r minus r over h x plus r. That gives you the radii at each place. So the integral pi r, which in this is going to be now the equation of the line, r minus r over hx plus r square dx. Okay, and you can just square it, integrate it, and so forth. So students don't like it because you have to do a lot of like algebraic expressions here, and it's not always friendly. But remember, capital R, lowercase r, and h are constants here. And then you calculate that. So you're going to get pi r minus r square over 3h square times h cubed minus 0 plus r minus r times r over h times h square minus 0 plus r squared h minus 0. So it's going to be pi r minus r squared over 3. And there's an h on top. H squared and h cubed cancel, I just get an h. Plus r minus r h plus r squared h. Oh, there's a pi that's missing. Yeah, very good. They all should have a pi. It's a little sweetness for everyone. Okay. And if you knew what h was and you know what r and r were, then you can just calculate that. Okay. Number 49 is a little bit, I guess, exciting, I guess. But once you see how it's done, then it doesn't really feel that bad. So there, actually, they're not giving you a coordinate, but that's what I'm going to do. So they're just going to give you a sphere. And then they're going to say you want to calculate the volume of the top cap. We call it a cap. Top cap of a sphere. And the height of that cap is h. The radius is r. You see a lot of spheres in this stuff. So there are different ways of doing this problem, but the way that I suggest you do it, that's how I'm going to do it. I'm going to put my sphere on the coordinate system. Actually, I'm going to call it that portion is actually a rotation of this. If I rotate this piece around the y-axis, I get that cap. Okay. So, well, what's the equation of this? Well, if it's a circle of a radius r, it will be x squared plus y squared equal to r squared. So I'm going to probably do the disk method for this one. So I'm going to be calculating, since it's floated about the y-axis, I'm going to be calculating integral with respect to y. Y goes from, the whole thing is r, and the cap is h. So it's going to go from r minus h to r. This is r minus h, this is r. The equation has to be in terms of y. So x squared is equal to r squared minus y squared. X is square root of r squared minus y squared. So it's going to be pi, and the radius is square root of r squared minus y squared, and then you square it, and that's how you calculate that. So it's going to be pi r minus h r squared minus y squared d. This method. Okay, so that's how you calculate the area or the volume of that little cap on top. Not very exciting integral. Let's do number 54. I think I may have assigned this one, but let's just do it together. Why not? And then we can have an understanding of while you're writing it up. So let's do number 54. So it gives you the base of, and I encourage you guys to look at the picture they're offering you, but the base of a solid S is circular discs with radius r and a circular disc. And parallel cross sections perpendicular to the base are squares. Okay, no problem. So I know my base is a circle of radius r. Very good. And then the cross sections are, let me just draw them like this. But each of those, if I take it out and look at it from the side view, it will look like a square. And you see the shape that they're introducing on page 448 for you guys. Okay, so, and this is negative r, this is r. The equation of a sphere is a circle, I'm sorry, is going to be x squared plus y squared is equal to r squared. Remember, the volume is integrating from left to right. The area, the cross-section area, now if it's with respect to x or respect to y, if I go left to right, it's with respect to x. If I go bottom to top, it's going to be with respect to y. And each side is going to be the distance from top of the circle to the bottom of the circle, or half of the distance of the x-axis to the circle. The distance of x-axis to the circle, and then double it. That's half of it. Once again, either you can calculate the whole thing or calculate this part and then multiply by 2. Whichever you like. Regardless, I need that equation. So y is equal to square root of r squared minus x squared. Again, what I did was y squared is r squared minus x squared, and y is equal to square root of r squared minus x squared if I just look at the top half of the circle. This is only half of the square's width side. So I have to double that. I have to square it to get the area of the square, which is going to be twice of square root of r squared minus x squared. That's the length. Dot square it, that gives you the area, and integrate it from negative r to r. And that's basically it. So just continue. Now it's an even function. You can use even or you can just plug it in, but it's an even function because you only have x squared. So you can just go from 0 to r and double it. That's a good trick to use as often as you can. Just make sure that it is an even function for this. So you have 2 4r squared times x minus 4/3 r x cubed from 0 to r. So it's going to be 2 4r squared r minus 4/3 r cubed minus 0. I've been clumsy with my equal sign. 8r cubed minus 8/3 r cubed. Okay. That is the result. Okay. I hope doing some of these problems helped you, but be patient with yourself. Some of these are gonna take some time to get used to, and that's why I moved sections around a little bit. Be patient with yourself. Ask me questions if you're not clear on it. There are other videos done better. Maybe you can look at those or look at my videos, no problem. And read the book carefully, because Stuart has a good way of explaining things, especially in this topic. So do take it. Don't do very especially difficult problems, thinking that if you know those, then you know how to do the easier problems. Work on the problems I assign, and then the ones I do in class. Make sure you understand the ones I do in class or in the videos, because I try to put focus on the things I think are important to you. So hopefully that will help you guys focus a little bit more for the understanding of the many things. Okay, if there are any questions or anything, let me know, but I hope this is a good start for your homework.